We want these spaces to be places that people want to be in.
How do we use technology to make buildings better?
So nowadays you can have anything at home really that can be automated through a phone app. All these different small electronics that are much more cost effective now than they were, a decade ago. At the commercial level, it's a similar trend. Building management systems for a long time were very, very expensive.
We see the value in that ability to monitor and get the correct data to the right people, but that should be part of that system's core. That should be part of what makes that system perform properly. It shouldn't be something that adds costs to the end user to get a system that operates the way you intend it to.
In today's video, we'll uncover exactly how we're using data to optimize the way buildings work, and how modern HVAC can benefit from remote monitoring and controls to improve comfort, reduce energy usage, and even fix critical issues in real time.
So if you have a failure on the busiest time of the year, we don't want the HVAC equipment impacting how your business operates in the most important time period. We want to resolve those issues quickly so it's not a disruption to your business.
I don't know about you, but I like a nice fried egg every morning. And although I like the outdoors and nature, I live in a neighborhood that specifically says I can't have my own chickens. So I buy my eggs at the store, meaning I know very little about producing eggs. Is that even how you say that? I don't know. But one person who knew about chickens was a Dutch mechanic named Cornelius Drebbel. See, back in the 1600s, pesky HOAs were probably not a thing, and Drebbel took advantage. He wanted to hatch chickens year-round, which meant in the winter he needed to keep those eggs pretty warm, but not too warm. He could have sat there opening and closing a vent to let some cooler air in, or adjusting the level of the fire, but
there is no time for that. There is no time.
So he invented this, a mechanism that controls the fire by opening and closing a damper based on the temperature of the water surrounding the eggs, using mercury and alcohol's expansion properties. This was the first self-regulating oven, the first thermostat, the first real use of automation, and the first man-made feedback loop, consisting of a regulated output based on the condition of an input. 400 years later, we still use this basic feedback principle to drive automated machines just about everywhere, from the smallest devices to entire buildings.
A building management system, in essence, is a computer program that is used to monitor and control different machinery within a building. So similar to how you have phone applications nowadays where you can track your home's thermostat, you have that also at the commercial and large building level. It's just a little bit more complex.
Historically, when there's a number of different systems operating on a larger facility and that owner wants to have some ability to view the operation of those different systems, typically this involves hiring a third-party controls contracting team that will review all the different systems in place, and they may have to install some of their own sensors, custom, or they may tie into the existing controls of those different pieces of equipment throughout the building, and they'll try to feed them all back so that they're communicating to some centralized controller and try to make some sort of a custom interface that the owner can then view and potentially adjust parameters on these different systems.
It is a feedback loop. You start at the very basic level with a physical sensor installed somewhere, and that small electronic signal that's generated by the environment gets translated through a different chain of events that lead it all the way up to a person that's physically looking at a trend, and then that person can take an action based on that trend.
Building management systems can be integrated for different applications and at different levels. From a convenience store, which may just need a comfortable space and an easy way to control the lights and security system, to a critical application like a hospital surgery room, clean room, or grow room, which all require extremely precise temperature and humidity control, as well as constant monitoring of the equipment.
Off-the-shelf building management systems don't know the details of how equipment is operating. So if you have a brand X building management system and a brand Y piece of equipment that's being monitored by that building management system, there are a lot of assumptions between those 2 points. And that doesn't present very well to customers. It doesn't show the customers how well the equipment's operating. So we have a huge advantage, a big competitive advantage of being the producer of the equipment and the monitoring system. We can paint a more truthful and accurate picture for the customer.
This is CASLink, our in-house, completely custom building management system that's tailored to extract the maximum out of our products. As a building owner, you're able to remotely monitor and control your systems and potentially the whole building from anywhere using only a web browser or our phone app. And as a company, we want to make better products. CASLink allows us to better understand and improve our systems. We can also troubleshoot and often even resolve issues remotely, which frees up resources and is a win-win for everybody. This software works with all of our products, but today we're choosing to focus on how CASLink is used to monitor and control our Paragon HVAC units.
Paragon is a product that's evolved over the years for us. And from the onset, we were looking at designing this around being a true dedicated outdoor air system, or a DOAS unit. Meaning, all right, we can handle 100% outside air, and everything needs to be able to modulate because we're dealing with very different outside air conditions at all times. And then when you're processing outside air, it has a lot of load to it, so you want to make sure you're using as little energy as possible. But what we've come to find is that this product can be used well beyond just these high percentage outside air applications. And even if you're looking at existing sites that need to replace equipment that's almost full recirculated air, there's still a lot of benefits that can be had by utilizing this kind of equipment. And it certainly has the capabilities. This unit can go anywhere from 100% outside air to 100% recirculated air in the building with no outside air. And with that, it can do it in a much more efficient manner than what you'd see on a sort of base level rooftop unit. But then from the controls standpoint, there are going to be challenges when you've got one piece of equipment that can do so many different things for so many different people.
The key to this flexibility is really in the amount of modulation that's built into Paragon. And while the unit is perfectly capable of running all on its own, having a tool like CASLink ensures that each modulating component is precisely tuned for the application. So I want to show you just a few of these data points, starting with the variable speed compressor. We can see data regarding its speed, temperature, oil status, and more in real time, or we can even go back and see what it was doing, say, last year. Moving on to the condenser, we've got readouts for pressures and temperatures, including calculated values such as subcool, as well as monitoring and control of the condensing fan speeds. We can see the status of the electronic expansion valve and correlate that data to what's going on in the evaporator coils with live superheat readings. For precise humidity control, we measure the dew point right after the evaporator. Supply fan speeds and CFM are also displayed, as well as discharge temperature and humidity. Of course, we may also want to know what's going on outside if we're bringing in outside air. So we've got readings for outdoor air temperature and humidity, as well as the position of the outdoor air damper, which we can control. Again, these are just a few of the data points that come in through CASLink. And when you've got this much data, it can be overwhelming for an end user. So we also have a dashboard, which provides a quick snapshot of each unit, as well as its basic set points. That way, we're able to provide a simplified view for users, while an engineer can access more specific, granular data. This data can be visualized individually or combined in order to better understand the interactions happening within the unit. And finally, anything that could be controlled by a technician at the unit's interface can also be controlled within CASLink. From simple set point tweaks to more complex parameters, an engineer can make remote changes and see how the system is affected in real time.
While CASLink has a lot of details and it monitors a lot of points in our equipment, we don't expect our customers to go in and look at every little data point. What we want CASLink to do for our customers is give them a bigger picture of how their building is operating, to allow them to make better decisions and the interaction between equipment and their building and their operation to be more seamless.
Units like Paragon don't exist in a vacuum. They're always interlocked as part of a bigger system. Like in this restaurant, the operation of Paragon will be tied to what this hood and exhaust fan are doing. If the exhaust fan speeds up, then Paragon would have to bring in more outdoor air to make up for the additional exhausting air. Now, the hardware required to run CASLink is included in the cost of Paragon HVAC, But you can also add this option to our other products for a low price. And we don't charge you any fees to access the software. So the only recurring fee for CASLink is a connection to the cloud, typically provided by a fixed cost cellular plan. For the price of just a couple tanks of gas per year, CASLink can provide a whole building view with all of these units under one interface. And this can even include products from other manufacturers.
RTU-Link is another product offering. This is a control board that's meant to actually interface with somebody else's rooftop units. Sometimes you might have, say, a restaurant where you have a Paragon serving the kitchen space, but then we've got somebody else's rooftop unit serving the front of house. And if this comes up, we want to try to have as much equipment under our monitoring view as possible so that we have the best holistic view of the building and how it's operating. We're talking a couple $100s to have a small control board installed in that equipment. And realistically, once you've got all the different pieces of equipment tied in, this can really be a full replacement for a true building management system. We've come across a number of jobs where the building BMS can be tens of thousands of dollars. CASLink simply offers more data on how our system's performing and has no monthly fees. So it's kind of a win-win from both sides. Every mechanical system is bound to have an issue at some point in the life cycle of that equipment. It's not uncommon for more basic equipment to just have a set number of, 10 faults that you may come into, and they'll have a different code that just says, all right, low pressure, very, very basic limited information. The normal sequence when you'd have a rooftop package unit go down would be, all right, let's call up our service team, have somebody come out, try and diagnose the issue. There's a chance that they'll figure out what it is on site. There's a chance that they won't, and they might have to go with the most probable issue based off of whatever fault code they see. They may or may not have that part on hand. If they don't, you have to go call, order up a part, wait for that to come in, set up a follow-up visit, change that part, and then just see if the system's repaired and if it works. What we want to do is, all right, if we have an issue, we want to see it in real time, go back and see what led up to that actual fault. And then from that, we can either find out if it's a setting adjustment that needs to be done, which that's a nice simple thing we can do remotely without even sending somebody out there. If it is something that's hardware based, it gives us an idea of, all right, it looks like this sensor or this component has failed. And then we can proactively order that part to our tech so that the first time they come out, they're coming out and they're going to be changing and fixing that issue on the first try. And by having all that past data to work from, we really have a good idea going into it what that issue is and keep that downtime to a minimum and keep costs down on that repair.
All right, so to start off, we're going to look at some examples of buildings that had heating issues. Heating is a little bit simpler than refrigeration, and I thought a good way for us to start analyzing the data.
We had a site where they were complaining that the space was overheating, but then it would get back to temperature. It was only while the heat was running that the space would overheat. And when we pulled back the historical CASLink data, what we found is whenever the heat would kick on, the discharge temps would be much higher than expected. Our system operates with a modulating heat. So as you turn on heat, if the space doesn't need that much heat, the discharge temps should be going down much lower. And what we're finding is the discharge temps were staying at like 100 degrees, even though the space didn't want heat at that point. So this was clearly an issue related with that modulating gas valve. We could see the software even wanted to pull that heat back, but it wasn't able to. So we knew it was one of two things. Either the gas valve itself, the modulating gas valve, had failed, or it just wasn't set properly. And when we sent our tech out there, they were able to come out with that valve in hand ready to go. But it turned out that all they had to do was just program that low fire setting. And once that was done, every time they called for heat again, you can see the pink line was those space temperatures creeping up and the purple was the discharge temps. After that point, every time we got a heat call, it was heating it to a much more moderate level and it was keeping a much more consistent space temperature as you expect. We got a call on a system. This was actually a system that wasn't even started up yet. They hooked it up to power and we were getting our CASLink data. And they were saying, hey, we just got this thing turned on in the meantime to do some temporary heating and it's overheating that space like crazy. So we pulled up the data and found, hey, our temperature readings are not at all where we expect them to be. We know what the outside air weather conditions are, and it was like 50 degrees outside, and our outside air temperature sensor's reading a number that's in the negatives. So this is a clear indication that there's a stray voltage going through our board that's skewing all the temperature readings. All of them are reading off. So we immediately pointed our tech when they went to actually do the startup to look at the field wiring of our space sensor. And what we found is they flip-flopped and wired our humidity sensor into the space temperature side and was feeding a stray voltage back. It was skewing all the numbers. So this was a very clear cut. We saw going into it, go out, check this. They changed the wiring in the field, and you can see the temperatures all came right back into where they expected once he made that change. So unless you're going through and actually reading that temp reading in the field, this would have been a very difficult thing that probably would have taken a few hours for a tech to diagnose versus it took them 2 minutes to go out, look for this, flip the wires back, and fix it.
For our final heating example, let's pull back a bit and see how the failure of another unit forced Chris to think outside the box to try to keep a store open using Paragon and CASLink in the middle of a polar vortex in Minnesota.
A dangerous and deadly polar vortex is sweeping the coldest air in a generation into the country's midsection. The upper Midwest will face temperatures 20 to 40 degrees lower than normal today.
It's a convenience store that had a prepared food section. And we had in the kitchen section a dedicated makeup air providing a portion of the makeup air for the hoods. And then we had a Paragon serving as the space conditioning as well as some of the additional makeup air for the hoods as well. What happened is, in the middle of this polar vortex, we had a scenario where the dedicated makeup air unit went into a fault, causing the heat to go out and then the freestat shutting that makeup air unit off completely. So at that point, we have a hood that's exhausting out all this air and there's nowhere for that air to be made up. We're pulling in air from any place that building can because we're going extremely negative pressure for that building. We had PSPs on the hood that were getting fed from that makeup air unit. And since that was going so negative in the space, that makeup air unit was now acting like a chimney sucking air back into that hood. And the temperature now was reading down to 27 degrees because that space was negative, and it's essentially dumping below 30-degree air directly into that kitchen now, as well as everywhere else in that building that it's pulling in negative 20 when the doors open. So the day that this went down, we got a call that the building's getting cold quickly. We pulled it up on CASLink. We saw the temperatures go from their 70-degree set point down to 58 degrees before we got that call for a service saying, hey, our space is extremely cold. Because of the polar vortex calling in all these different techs, we couldn't get a tech out there until Friday. And they're expecting to hit the lows of this polar vortex on Thursday, so in that window. So we know we're facing a situation where they're going to potentially have to shut that store down completely if we can't get a resolution.
Looks like she's gonna turn cold tomorrow.
Oh, yeah. We got a front coming in.
Yeah, you got that right.
So what I did when I pulled this up is I actually pulled up both the makeup air unit, the hood operation, and then our Paragon unit's operation to see what's going on at that real time. My goal was to try and reduce that negative pressure as much as I can. So we got a little bit creative here because I can't get out to this site and actually measure where we're getting negative pressure or we aren't. So again, this Paragon unit was designed to run at a certain percentage outside air, not 100% outside air. So my goal was I want to keep increasing the outside air and increasing that damper position to bring in more and more outside air until we get to a point where that building is neutral. And then at that point, hopefully we're not bringing in that super cold air, and that unit serving the front of the space can now maintain the space temperatures better. So what I did to track this is I slowly started increasing that outside air damper by about a half volt to a volt in 2-minute increments, and then tracking what the PSP temperature sensor in that hood was now reading. Because keep in mind, if the building is negatively pressurized, air is going to be coming in, so that PSP reading is going to be very cold. Now, if we get to a point where we're actually getting slightly positively pressurized, now air from the space should be going up through that PSP, so our temperature should be reading closer to what that space temperature is. So I kept tracking that up until we got to a point where that outside air damper was reading a PSP temperature that looked like the space temperatures. And at that point I said, all right, we are now space neutral. So this shows now, once I started adjusting, this red value is that outside air damper. You can see I actually brought it too much positive, started dialing it back, and I fine-tuned it up, down until we got right to that balance point. And then with that, I wanted to also make sure that my discharge temps were adequate. So at this final point here, we can see my discharge temps were still able to hit, even with that added outside air over what the unit was designed for, we were still hitting around 100 degrees. So this space in the end had no compromises. This was at a time when the outside air temps were negative 20 degrees. And with that dedicated makeup air unit down, we were able to make up that same amount of outside air on the Paragon, had enough heat to still maintain those discharge temps. It got us by. We changed the operation of the unit from how it was intended to operate, but we could see what the root cause was and get them to a point where we could keep them running until we can get a tech out there to actually repair the final resolution.
Being able to troubleshoot, remotely determine what is happening in the equipment is a very powerful tool because it eliminates guesswork. First of all, I don't know how many times we've had service companies go to our equipment and just start replacing components because they don't know what's going on with the equipment. Meanwhile, the customer is not satisfied because their building's freezing cold or way too hot. So the service company's just wasting time trying to guess at what's wrong with the equipment. It's more of an exact science with CASLink. So we don't expect our customers to know all the little logic details in our equipment. What our customers want to see is the equipment working and is it maintaining good air quality and good building conditions? And we show that in a quick summary on the dashboard. If, for example, we want to know the nitty-gritty detail of how a piece of equipment is working, Captive Air experts can help our customers work through those issues and work through those challenges and provide as much or as little information as they would like. Some customers have actual facilities teams that want to take on that responsibility of maintaining their equipment. When that is the case, those customers have full access to this data and alerts. So for example, if a unit needs to have its filters replaced, we can issue a clogged filter alert.
You can set up these email alerts to any third-party service you want. At the very least, our own sales team and our own support teams will always be outfitted with those email alerts automatically for any system that's sold and set up. So that way, we make sure that on every single job site, if there's an issue, at least somebody's getting that email alert. And if it's a critical issue, we can get proactive and start reaching out to that customer. Oftentimes, we'll reach out to try and set up that site visit before the customer even realized that the unit had a fault.
The name of the game here really is being proactive. And this is actually quite a big departure from what's normally done in the industry when things go wrong. But the question really becomes, how do we take this mentality beyond just fixing issues? Because really, we can leverage this data to do way more than that. A few months ago, a large pizza chain owner contacted Captive Air with an issue that had nothing to do with comfort. The owner had several locations that had been outfitted with Paragon units, and he was happy with the performance in all his stores, except for this one.
We were seeing higher electric bills than even what he's seeing on his non-Paragon restaurants, which is obviously surprising. We would expect, even in different climates, that there should be enough of an improvement on energy efficiency with using Paragon over a more traditional basic low efficiency unit.
Okay, so now it's actually time to use CASLink to figure out just what's going on here. And I feel like I have to say that Chris wasn't originally the person that resolved this issue. And although he knows how it was resolved and he understands that, he's never actually looked at the data himself. So this is a pretty good opportunity to get a glimpse into how an engineer might go about resolving an inefficiency problem like this one. The first thing he'll do is use NOLA, our internal specifying and quoting software, to find out a little more about the setup and intended operation of the unit in this particular building.
It's serving as the primary space comfort for heating and cooling for this space, but also serving as the makeup air for the hood. So this unit runs at around 50% outside air. It's going to be interlocked with the hood system, and when it's on, it's running that 50% outside air versus when the hoods are off, it's going to be running full recirc air. Constant volume, no modulation. So it should be pretty straightforward in trying to review how the system's meant to operate. So I've just pulled up, let's make sure this was the right site.
In troubleshooting, they always say, check the easiest and most obvious thing first. So Chris will do exactly that. He'll check the occupancy modes and scheduling first to make sure that the unit isn't running at night when nobody's in the building.
That is a quick and easy way to waste a lot of money if we find out that somebody's turning these hoods on or the schedule wasn't set up properly and these things are running 24/7 instead of only during these occupied times. So obvious, very quick and rudimentary way to check this is you can just go back and check to see, are we going into unoccupied modes? Now, we need to go back a bit to see at the time of the actual concerns what we were having at those times. So let me go back. All right, I can see that we've got a window here for Friday, but that goes all the way through Thursday. So we would have expected at that point to be going into unoccupied modes. Now, I'm guessing it's likely because of the interlock, but let me see. All right, so I can confirm it's going into occupied because of that interlock with the hoods. So this is certainly going to be a big piece of energy wasted. If we pull up our damper, we can verify that this thing's going to be processing a lot more outside air, and it's also, while it's occupied, keeping that fan running continuously. That's going to be a lot of wasted energy just from the outside air portion, as well as wasted fan energy that they simply just wouldn't need during these times. So that's going to be one big piece of it. But the other thing I'm curious about is during the audit, it was noted that we were running with too aggressive of a dehumidification set point, and we were actually overshooting our humidity set points. And I'm going to change off the occupancy here. More what I want to get into now is focusing on the comfort and the humidity of that space. So I want to see during our occupied times, what's our space dew point set point? So we're targeting a 52 dew point in the space. And then I want to see what the actual space dew point is reading.
Note here that the space dew point inside the building is often way lower than the set point of 52 degrees, and by some margin. If this is because we're over dehumidifying, this would be a huge energy waste.
You could have times where we're below that space dew point set point because the intake is dry. If you're in a climate where it's very dry, that's not an issue, but we want to make sure we're not causing that dew point to be below the set point because we're running our compressor more than we need to. So what I'll plot in here is I want to do a check to see the intake dew point to see if it's anything above that 52 set point, and then we're coming out with a space dew point in the 40s. That's because of our unit dropping that dew point of the space and essentially over dehumidifying. And that's exactly what we see here. So we have a lot of options on how we can adjust our dehumidification to react based on space conditions. But essentially what's going on here is this unit was set up by default with a more simplistic dehumidification logic approach. It was saying, all right, if your dew point goes above this value on the space side or on the intake side, we activate our dehumidification logic. But at the most simplistic design, that unit is just going to say, all right, anytime there's a dehumidification call, I'm hitting X dew point off of my coil. And usually if that's how the system is set up, which is very common for dedicated outdoor air equipment, it's going to shoot for whatever the worst case coil temp it needs, the lowest dew point it would need to cover itself on the most humid days. But any other day that is not that peak design day, if you activate because of intake, you're going to be over dehumidifying and that space will be below your dew point. But as long as the humidity is high enough to keep that intake activated, you're just going to keep dehumidifying that space further and further. And you result in a situation like this where now our compressor, if I plot my compressor speeds in here, we might be running at 3/4 load where we could have been running at half load on that compressor. We'll pull it up and actually take a look. We're running at full compressor speed much of the time here, 200 hertz. So hey, if we could have been running that compressor at half speed to just dehumidify to whatever that space dew point is only, that's going to save us a lot of money. So we have a feature that does allow us to track that space dew point and then hone in our coil temps to hit exactly what the space needs to maintain that set point. This is called a dynamic dew point adjustment.
Dynamic dew point gives us the ability to modulate how much we dehumidify the space, just like we're able to modulate how much we sensibly cool it. Looking at the psychrometric chart, this cooling curve shows cooling to a fixed, worst case scenario dew point. This much latent cooling may be needed when the internal heat gains and sensible heat ratio require it. But in less than peak conditions or when the SA chart changes, it ends up causing an overly dry space. With dynamic dew point, we can adjust how much latent cooling takes place within a range, and the unit will actually monitor the space conditions and adjust the dew point accordingly. If this is at all confusing to you, that's totally understandable. We've actually made 2 different videos covering these kinds of topics. The main one would be psychrometrics, And also we did one on load calculations. That one might be helpful as well. And I've left the links in the description. We'll go into why this feature wasn't originally enabled later on the video, but for now, let's look at what happened when we did activate dynamic Dewpoint.
Already we can see as it's starting to zoom in. So this compressor speed, which is sitting at max speed, is now running, you know, closer to 50% capacity in many of these cases. And then with that, you can see that purple space dew point, that now goes right back up. And with that, it looks like they also noted, because I was gonna say when we first looked at this, 52 degree dew point for a kitchen, that's pretty low. You know, even if we're trying to target maximum comfort, 52 is a pretty dry kitchen. So another spot for some savings, they bumped that set point up from 52 to 54, but you can also see a drastic change in the actual space dew point going from the 40s back up into that 52 up to 54 range. So this is a really good improvement here where that purple line went from below whatever the set point is up to the actual set point of the space. And then we can see that compressor speed went from very high speeds down to much lower speeds. That translates to the comfort is still gonna be there, but we're gonna be spending a lot less energy to maintain that comfort of the space.
Before adjustments were made, we were seeing power usage around 13 to 16 kilowatts. And after, we're averaging about 6 to 8 kilowatts. You pay your electric bill based on kilowatt hour usage. So in this case, we can say we cut the compressor's energy usage by almost half, which is actually a huge deal because the compressor is the biggest power draw of the entire system. When you put this together with the findings about occupancy scheduling, we estimate that the total savings for this user using our recommendations is upwards of $1,000 a month. But would we have noticed any of this if the owner of this pizza chain hadn't compared his energy bills? And could it be that a lot of other units out there may be experiencing the same hidden inefficiencies?
Usually, no news is good news is sort of how people approach heating, cooling equipment. The best compliment you can get is that somebody isn't calling you up to complain, because if they're complaining, then there's an issue. But you're not gonna get, hey, my room is the temperature you said it was gonna be. A lot of times engineers will specify a new piece of equipment, but unless there's like a major issue, they're not getting pulled in after the fact. They are not going out and seeing these sites and seeing how things perform.
Right, so in light of this, Captivair's been implementing some different steps to ensure that we are, in fact, using all this data.
We always want to make sure when we set up a unit that we have what's called an SDV, a system design verification from one of our own in-house service techs. They're factory trained, they know these units very well in and out. But we're extending those services to actually look at system performance after just that day one setup. So we have this new team, it's called our Connected Commissioning Team, our CCX team, where they offer continued monitoring services and support. So they'll do an initial audit on these job sites a few weeks after the initial SDV, just to make sure nobody else has changed settings. This is now still working the way it was meant to. It's just sort of a double check. The next check will be once we get into around a month of operation into a heavy heating or cooling season. And then we'll also set up a follow-up secondary audit for whatever the opposing season is. So if we do our initial audit in the peak cooling season, we will do the next audit in the peak heating season. And then once we've gotten through both seasons, then you've got a pretty good idea of how this unit's gonna operate in every one of these different types of conditions.
Each audit concludes with a custom report, including a summary of the survey findings, set points and settings, and other assessments that ensure heating and cooling are working correctly, that the humidity is well controlled, and that unit cycling is kept to a minimum.
They'll tap into screenshots of actual performance in CASLink versus what we would expect operation to fall in versus NOLA. So again, we're making sure is this unit operating at the right outputs versus what we would expect for capacity.
Customers expect high levels of comfort and efficiency in their buildings. The last thing you want to think about is what's the refrigerant pressure and temperature in this unit at 7 o'clock in the morning. What they should be thinking about is how do I make my operation more efficient and how do I make my building more comfortable for my customers. Looking at the pizza chain example specifically, we want to make sure all that equipment is running at peak performance. So our CCX team ensures that that equipment is being reviewed and upgraded, operating at that peak efficiency.
At the smallest level, we could view our one piece of equipment. We can verify the unit's doing what we expected, but we have so many other pieces of equipment that are operating in that same facility that we also want to have that ability to tie them all back into CASLink and see as a whole, what's this building doing? Because again, even if our one component's working right, if another component's doing something that we weren't expecting, it can have an impact on that initial component. So we need to look at that building as a whole, but then even at that level, we might have a specific chain. We can compare, these are the same footprint building, but we're in one climate versus the other. How much energy usage are we using on one versus the other? What's our optimal comfort set points for this location versus the other? What's our average run time for equipment on one location to another? So we can look at all the way down to an individual unit, to that building as a whole, to also a chain or multiple facilities in different parts of the country. And then at the biggest level, we can, as a manufacturer, take a look at all of our equipment operating across the country and say, hey, is there an inefficiency that we found here where we can improve on our logic, or can we improve on a sensor that's going to minimize downtime if we're seeing trends at a larger level?
As time goes on, we get better at producing and designing equipment. So we make constant improvements in the software. What CASLink allows us to do is provide updates to equipment to not only keep the equipment operating reliably, but we can actually improve the performance and efficiency of the equipment with remote updates year after year to make it more productive and more efficient.
The dynamic dewpoint logic we talked about earlier is a perfect example of this. The team found an over-dehumidification trend in multiple units across the country using CASLink data, and it stood out enough to take action and develop this newer logic. Then all we had to do was implement this feature via a simple remote software update. And this is actually what we did with the pizza chain location.
That was that exact example. We realized that one of the units weren't configured with this option, and we identified that, and we're able to upgrade the equipment at no cost to help the customer be more efficient.
Dynamic dewpoint became crucial when we started using Paragon in grow houses. Plants require extremely tight temperature and humidity control, which means to this day we continue to fine-tune and improve the software and logic driving these units. Another huge testbed for us were and continue to be the affectionately named Luddy Schools, a series of private academic facilities established by Bob Luddy, the founder, owner, and president of Captive Air.
When we first started rolling these out, there were a few of us that were going every single morning and looking at any complaints from the staff, from students, and every morning we were dialing these things into CASLink. And to be honest, we learned a lot from that just on also even where set points are optimized. One example would be every person seems to have a different perceived temperature level or humidity level where they think this is comfortable to me. So like ASHRAE gives you these windows of, all right, this is the comfort window if you're somewhere in here, but you still get one person to the next. One could be comfortable in the space, one could not be. So you want to get as many people in the group as happy as you can. What can we do to minimize the number of people who are uncomfortable through the space? So first we're saying, hey, can we go cooler and cooler in the summer? Is that going to help? But then some people are getting too cold. The best thing we found was actually dropping the dew point lower than what you'd typically be trying to shoot for on a space. So a normal occupied space, people are often trying to shoot for like around a 55 dew point. We started to find is more like the 51, 52 degree dew point, sometimes even a little bit lower. It's a higher energy use, but then you can have a wider variance of temperature before people start saying they're hot or cold if you start wringing the moisture out of the air a little bit sooner. So without CASLink, we'd have no idea, what the best combinations sort of fall.
Experimentation and the engineer's intuition seem to definitely have a place when analyzing so much data. But as more units come to the market, how do we make sure that we have enough resources to effectively put this data to work? The answer is machine learning. And I know that may seem like a lot, but actually the way we use machine learning can be quite simple. For example, we have this data here showing the temperature inside a kitchen hood duct. We can see that it fluctuates quite a bit, so when the temperature is higher, it means the cooking appliances underneath this hood are in use. Every day the temperatures rise, they hit a peak, and when the kitchen closes, they come back down. This pattern is predictable, so we would expect that the exhaust fan speed would follow this pattern or at least have some correlation to it. But in this case, it doesn't. It stays on at the same speed for days. Whatever the cost, this is a problem that wastes energy. And just like you and I were able to detect it just by looking at the 2 lines of data, we can use machine learning to teach computers to basically do the same, then notify the right people.
Just looking forward, we want to apply predictive analysis on equipment and be able to predict when to service equipment or be able to predict when a component may be ready to fail and address that issue before it becomes very disruptive for business owners.
Especially things that are repetitive. You know, if you have a team of engineers that are constantly trying to optimize the operation of HVAC or any type of machine for that matter, the fact that we have all this data and the fact that we have so much computing power to manipulate that data to will eventually allow us to just automate some of the actions that are taken and have our engineers focus on different types of things. And I think this is something that's not just in the HVAC industry, but in pretty much every industry that has the same type of devices out there. It's just going to lead to more and more optimization.
From perfectly hatching eggs to using nationwide data, these feedback loops have certainly come a long way, and they're improving every day. On a more personal note, it feels really good to be part of a company that develops a tool like CASLink and offers it at what's really just the price of the connection. I know it's easy to be skeptical about products like these. I know I was a little bit, but after making this video, and hopefully you after watching it, I can definitely say that having this much data in such a well put together package is 100% a benefit to the building, to the people in it, and to the equipment itself. So what do you think? Leave us a comment, let us know, and as always, thank you so much for watching.